welcome to this new video where I'm going to show the result of the last, say, 3 or 4 days of work, where I have re-engineered the strip of my project, moving from the microchip Atmel platform to the STM32 platform. But before to start showcasing what I've done and the reasoning that was behind this re-engineering, I would like to kindly ask you to subscribe if you haven't done yet, to give a thumbs up to the video if you like it, and to hit the bell as usual. For you it's a small thing, and for me it's very important because it helps me in sustain the channel and keep on producing and uploading contents. So why I have re-engineered the strip, which was fully working in the version that I have already shown in several videos in the past. But I would say for 3 reasons. The first one is because I am moving, as you know if you have seen the other video, from the microchip Atmel platform to the ST platform. So I have already developed the main board for my DIY MIDI remote control with the STM32F072 microcontroller. I have recently developed the master fader of the surface with the STM32F072 microcontroller. Check out the last 3 videos that I've posted to see the work done. And so it was very inefficient to have part of the surface working with the technology, with the platform, and part working with another one. So I mean, in this way I'm gonna fully move the project to the ST platform. This is the first reason. The second reason, very banal one, I am very happy about this STM32F072 microcontroller. It's working very well. It's rich of feature, it's very stable, it's very powerful. It's based on Cortex M0 Plus processor, like the SAM-D21, which is the microcontroller that I used on the old implementation. But I have to say that I really found this microcontroller better, quote unquote, in terms of, again, performance, flexibility, stability. So for all these reasons, I find this microcontroller very intriguing and interesting in order to move the strip to this new platform. Just one important thing to say is I am not saying by any extent that I think that the hardware of the microchip Atmel MCU is better or worse than the ST one. What I'm just saying is that my implementation, my software, the STM32 one, say, came out better. Okay, so I mean, maybe it's just my fault, but that's it. This was the second reason. Third reason is related to this guy here, the rotary encoder. If you have followed the development of the old strip, you know already that I had a problem at the time with the rotary encoder. Substantially what's happened is that when the strip was fully loaded of work, of data coming from Cubase, so when the ADC was reading in order to read the position of the motorized fader, the PWM, so the timer PWM was working in order to control the movement of the motorized fader. The touch was running in the back constantly in order to capture eventually my touch. The LEDs here, the meter bar, the rotary encoder LEDs here were going on and off because there was in Cubase some automation registered. So the control of the shift register, I mean, the full functionality was running with automation, and I was trying to record some automation on the rotary encoder. This was not working very well. It was not smooth. It was moving in a little bit uncontrollable way. This because probably the MCU was really incapable to manage everything in a solid way. At that time I tried several solutions. I mean, on the asynchronous thread, so using the external interrupt. On the synchronous thread, trying to decode the quadrature encoding on the main thread, but I never came to a good result. It was actually quite ugly. For this reason, in order to resolve, at that time I decided to add a second microcontroller, a STM32F072, that was actually reading as only a main task the rotary encoder, and then communicating the result to the main MCU, the STM32F071, via UART. With this trick, I managed to resolve then the rotary encoder registering recording of automation was working quite well. Of course, I mean, as you can understand, the drawback of this is that the circuit gets more complicated. You have one microcontroller, additional microcontroller added into the circuit that you have to place, that you have to test, that you have to assemble and program, and so on and so forth. So I mean, it was clearly, and you have also to buy because it's a cost. So it was clearly a complexity more. At that time, given that I spent a lot of time trying to resolve this problem, when I found this solution, I decided to stop there and I developed it like this. But I always had in mind that there was a inefficiency over there in terms of the circuit. Here I have fully resolved the inefficiency, so eliminating the additional MCU. How? I used the encoding feature of the timer counter of the ST microcontroller, which is an available feature that you can use to decode the quadrature encoding of a rotary encoder in a hardware way. So substantially the hardware, the timer counter, does everything. Even you don't even need to add an RC filter, for instance, so a resistor capacitor filter, in order to make stable the reading of the rotary encoder. The timer counter does literally everything. And the result is really very good. And in my case, with this trick, I fully managed to resolve the problem. So as you will see in a moment, now you can run the strip all feature and at the same time record some automation on the rotary encoder, and everything works fine. So let's see. As usual, I run here my project. As you can see here, you have the meter bar, which is reacting according. The rotary encoder is set in the middle for the moment, and moving here, I can easily move and correctly move the fader. The touch is working perfectly. So now we stop and we start recording some automation as usual. So I put in read and write here, I run, and voila, I start recording automations, just touching, and there you go. I stop, I get back, and here I have my automation recorded, and I have my fader which is autonomously moving. And now we stop, we go back, and we try to record automation also on the rotary encoder, which is the thing that was not really working with the old platform. So I do this, and there you go. And as you can see here, the pan pod feature is perfectly smoothly working, and is also very precise. If I move just one value at a time, it's perfect. So now going back, I run everything, and you see the fader moving, and you see also here the lights, the LEDs moving accordingly to the automation recorded into the rotary encoder. So it's working very well, and I have one microcontroller less, so one IC, programmable IC less into the circuit, which makes the circuit more clean, efficient, and cheap than the old one. just one additional note again on the rotary encoder. As you can see, I can really move one value at a time, or I can accelerate and move quickly more values. This is something that I have developed with a timer. I have a timer inside which is running every millisecond. As soon as there is an event on the rotary encoder, I'm attaching to this event a time, and when the second event comes, or the following event comes, I make an evaluation. If the event is happening after more than 100 milliseconds, I just move one position, one tick as a time. If it comes shorter, so if it comes at 50 or 30 milliseconds, it means that I'm moving the rotary encoder in a faster way, and so instead of incrementing just one value, I'm incrementing either of 4 or of 9 value, and this produces the sense of acceleration when you accelerate moving the rotary encoder. It's working really super. It's really very nice, and the sensation moving is really super professional and super precise. Final point again on the optimization of the circuit. What I'm gonna do now is I'm gonna redesign the PCB. The PCB will be just one unique PCB. What does it mean? It means that this is the old implementation that you have already seen in the other videos. In this old implementation there was 3 PCBs. You see one here, the bigger one, with the buttons, the LEDs, the rotary encoder. You see here and here 2 shift registers which are controlling these lights and these lights. And you see here the additional SAMD11 microcontroller that I was mentioning. On the other side here, as you can see, you have here, I don't know if is visible, is this one. This is the SAMD21. And you have here on the opposite side you have here, I don't know if it's possible to see it, yeah, it's here, the voltage regulator. So this is the first PCB. Then you have a second PCB here, which is the one attached to the motorized fader, where you have here the motor control, which is attached to the SAMD21 PWM. And finally you have the third PCB here, the red one, with 2 shift registers here and the 14 LEDs here for the meter bar, again connected to the SAMD21 here to control the shift register. So it was 3 PCBs with the, by the way, 3 PCBs with a lot of cable, as you can see, work to be soldered and managed. With the new one here, you will have just one single PCB. The PCB will go straight from the top here of the strip, and here will enter like this and will cover here the LEDs here. The motorized fader will not be the one with this interface, which is called PC interface, the one where you solder the PCB. What will be with another interface which is called snap-in, which is just a GST connector that you connect and you quit from the cable that I will attach to the PCB. So also on this perspective, the result will be more efficient because there will be just one PCB. I will have any way to resolder everything, but I will have much less cable solder work. It will be cheaper, okay, because instead of producing 3 I will produce just 1. So again, a more clean and efficient result. But that's it. I will see you in the next video where I will hopefully show the PCB that I will have produced, the new PCB that I will have produced. Thank you very much and see you.